I can tell you that what it takes to be effective in Python is pretty straightforward. To be effective in Python, that requires a certain understanding of a couple of core mental models of the language, an understanding of some of the things that the language comes with, like the built-in data types and the built-in functions, a little bit of an understanding of what's available in the standard library. This talk, however, is focused on the next step. What does it take to be a little bit better than just effective? What does it take to be good at Python or an expert at Python? Now, I could spend the next 2 hours telling you in very philosophical terms what that means. And I could tell you why Python experts do things in one way or the other. We can even go very deeply into some of the meaning behind the Zen of Python. But instead, what I'd like to show you more specifically is a couple of what I call perhaps metaphors in programming in Python. It turns out that, as many of you know, Python, though it originated as something of kind of a scripting language, just a convenience language to patch together or to orchestrate code that was written in C to write simple scripts, has since grown into a full-fledged general-purpose programming language. And along the way, it's developed its own ways of thinking about certain core constructs in programming. What I'd like to do in the course of this session is show you 4 features of Python and the ways that an expert would think about these features. What I want to show you is not the syntax of these features. The purpose of this presentation is not a feature parade. It irritates me endlessly whenever I see somebody who's writing a book about advanced Python, and the entirety of the book is chapter 1, here's a feature. Chapter 2, here's another feature. Chapter 3, here's a third feature. And the entirety of the discussion of these features is merely its formal characteristics. Oh, a generator has a yield instead of a return. Oh, you can't send a non-none value into a just started generator. A lot of fundamental details of how these features work, but very little talk about how we can conceptualize these features in the broader sense of what they mean for modeling core problems. And so what I'd like to do is I'd like to talk about 4 of these features that you may have seen before, and a couple of the core mental models for how you can think about them and how you can think about Python as a whole and wrap all of these together. One thing that you'll notice is, in addition to, you can probably hear I'm a little bit stuffy and a little bit sick. That's only going to exaggerate my inability to remember the syntax or the documentation for basically anything. So you may see me stumble, but part of this presentation is to see me stumble and to understand that in cases where you don't understand or you don't have the documentation memorized or some of the corner cases memorized, what really is more important for all of these features is an understanding of what they are and what they mean, and not so much all of the implementation details. Those implementation details are, of course, critically important when you're using a feature, but that's information that you can look up and refresh when you're actually in the middle of using that feature itself. Before I get started, I'd like to take a small informal survey of the audience. So how many of you here are Microsoft employees? Almost everyone. How many of you are Microsoft employees that use Python as part of your Microsoft work? How many of you are just Microsoft employees that have seen Python used in various areas of the company, but don't really have direct interaction with it yet? How many of you consider yourselves to be pretty okay at Python? How many of you consider yourself to be really good at Python? A couple people? How many people are already in the back of the room thinking, I should be in the front of the room giving a talk myself? Maybe one person in the front. Okay, maybe we'll have to show you something new. When it comes to those of you who've seen Python, how many of you feel like you're pretty effective in Python? I can give you a simple problem, you can write some functions, maybe even write a class or two, and you could solve the problem without too much sweat. Is that most of you? How many of you are complete newbies, and you're like, I have no idea how to even get started with Python? Okay, for those of you who are complete newbies, you may struggle a little bit. Part of this talk does presume a baseline of understanding of Python. However, I don't think that the core lessons that you'll pick up here are lessons which will be totally lost on you. There are a couple of core lessons which even those of you who are somewhat effective in Python already may yet have internalized, and we might have a little bit of time to repeat those. What I want to start with is, I'll start with something really, really, really basic. And I'm going to start a little bit more basic than what I had planned to, just because I thought the audience might be a little bit more advanced than that. So what I'll talk about at the very beginning is something that we might call the data model. Now, what you'll see is I have all of the materials for this prepared and memorized in my brain. And unfortunately, my brain is getting older and older as time goes on. And so I've already forgotten exactly what I want to talk about. And so you'll see a little bit of roughness here. But part of the purpose of this presentation is to present you with just the information that matters without a lot of the distracting details. And so I will actually rewrite all of my notes for this as we go. It's going to be a little bit rough, but hopefully it'll be an opportunity for us to focus just on what really matters and for us to put aside a lot of the associated implementation details and things which, frankly, it matters when you care about them, but it's not part of that core lesson of understanding Python. I want to start off with something very simple. And you can see I created a directory called data model. And I'll just create a simple file in here. I want to create a class. And we're going to do all of this. Everything in this course will be, or everything in this session will be in Python 3.6. It'll be in Python 3.6 just for my own convenience, just so that I don't have to worry about all the details that might differ between Python 2 and Python 3. There's no particular reason why I choose Python 3 versus Python 2 for the purposes of what I'm going to show you, other than it's the Python that I happen to use, and it's the Python that happens to be, there's some political reasons behind why Python 2 or 3, but even skipping that, it's just for my own convenience, it's just to simplify things. So let's start with something very simple. I have some class. I want to do some kind of mathematical operation. I have some piece of software I write, and I have some class here that represents a polynomial. Some simple, linear polynomial with various coefficients, and I want to represent it as a Python object. And so I start with some code that looks like this, right? Class polynomial doesn't have anything interesting in it. And I can create two polynomials very simply. Right? And I might say P1 has coefficients 1, 2, and 3. Right? So this would be x squared plus 2x plus 3. And P2 has coefficients 3, 4, and 3. So this would be 3x squared, plus 4x plus 3. Okay? And I want to be able to do some simple things that we did in math class with these. I want to be able to add them. I want to be able to subtract them. I want to be able to figure out some details of them. The very first thing, for those of you who are relatively effective Python programmers, is you're going to look at this and you're going to say, why on earth did he write that in 4 lines when he could have written it in 2 lines? Why did I write this in 4 lines here when I could have written it in 2 lines? How would I compact my code here? So instead of constructing my 2 polynomials and then initializing the coefficients, I could initialize them all together. What would I do? I'm trying to get you to give me a little bit of feedback here. So what would I do? What am I missing here? My class has nothing in its body. What is it missing to allow me to do this a little bit more conveniently? A little bit louder for me. I need an init method. And so the very first thing when some of you look at this is you say, hold on, you're wasting our time here. You probably want to have an init method that looks something like this. So you can write these lines much more tersely. And you don't have to have 4 lines when 2 lines would do. All right? So now we're happy. Whoops. So now we're happy. Now, if I run my code, and I'll split my screen, shrink this a little bit, and I'll maybe print out, actually I'll do this. So I'll run my code, and I have P1 and P2. And then somebody else looks at this and says, oh my goodness, printing out to the screen, that looks so ugly. What am I missing here? I'm missing another method. What am I missing? I'm missing a method that corresponds to what happens when I call this function at the top level repr to figure out the representation of my Python object. Yes or no? Yes. So what method do I implement up here? I have some method called repr. Right? So I have some method here that returns a string that gives me the information, gives me a printable representation of this class to the screen. And so I'll make this very easy. Like that. And so I'll run my code again, and we'll see Oh, there we go. Those are our two polynomials. Pretty straightforward. And we could make this printout a little bit prettier. We could see the x squared and the x and the constant term if we wanted to. But you can see this is a lot easier than just seeing the name of the class and its memory location. And we can continue down this exercise, because the next thing I want to be able to do is I want to be able to add these together. And when I add them together, nothing happens. Python gives me an error. Unsupported operand types for plus, polynomial, and polynomial. But that doesn't make any sense. I know I can add polynomials. I did it all the time when I was in high school. How do I tell Python how to add polynomials? I have another method called add. And in my add method, I might return a brand new polynomial where I just give it all of self.coeffs, they're not coeffs, where I just zip together and add each of the individual items. So when I run that in my script here, p1 plus p2, it gives me a polynomial with 4x squared plus 6x plus 6. Now, what's the pattern that we see evolving here? For those of you who, off the top of your head, you didn't remember which of the underscore functions there are, for those of you who haven't ever seen these underscore functions before, you've begun to see some pattern. And what is that pattern? I have some behavior that I want to implement, and I write some underscore function. Some function that begins with 2 underscores and ends with 2 underscores. And for those of you who are Python programmers already, you might be familiar with these underscore functions. You might call them dunder methods or double underscore methods. Or if you find that word abhorrent, as I do, you might call it by a different name, data model methods. And you might say it's an absolutely absurd thing to call these data model methods. That's so many more syllables than dunder methods. But there's a reason I call them data model methods, which is, and I don't think I have internet access, but maybe I do. Oh, I do. If you Google for data model in Python, the very first or second link, depending on whether you use Bing, Google, or DuckDuckGo, will be a piece of documentation here that tells you all of these methods and what they do. But the pattern is a little bit more interesting than that. It's more than just having all of these methods on a single piece of documentation. It is that whenever we want to implement some behavior in Python, we want to tell Python, for this arbitrary object, do this behavior. Give me something that is a principal representation for this object. Perform some notion of addition for this object. We always see this common pattern. And the pattern is as follows. There is a top-level function or some top-level syntax. And there is a corresponding underscore function. The exact arguments that that underscore function takes will be determined by whatever you find on this documentation page here. The default names of the arguments you can pick up off this documentation here. So for add, I called it self and other. That's just the conventional names for this. What each of these actually do, you can read from the documentation. But there's something more fundamental here. There's a pattern. When I want to add 2 objects, I implement add. When I want to initialize an object, I implement init. When I want to tell Python what to do, when you call repr on an object, I implement repr. We know in Python there's a function called len. It gives you some notion of the size of an object. What would it make sense for the size of a polynomial to be? What might that notion be? Any thoughts? The degree, right? The highest degree. So we want to implement this notion of size on this polynomial. How do we actually implement it? What's the name of the underscore function we have to implement? The one hint is there's usually a very close correspondence here. So what would it be here? Len. If we wanted the exact arguments and any of the caveats for how this needs to be implemented, we could look at documentation. There isn't anything special in the case of len. And we just return something like len of coefficients. So this would tell us the size of the polynomial in terms of its degree. And you can see these are both degree 3 polynomials. The pattern that we see is as follows. The Python data model is a means by which you can implement protocols. Those protocols have some abstract meaning depending on the object itself. In the case of a polynomial, to add them means whatever that meant in math class. In the case of a polynomial, to find its size means whatever that would make sense for the case of a math class. So it may make sense for us to know what the size of this polynomial is in terms of its highest degree. To get its representation, its principal representation, has meaning that's given to us by the documentation. The representation of any Python object is typically whatever string we'd have to type at the console to create another instance of that same object, and so on. In each case, this protocol exists. There is some underscore method that implements that protocol. There is some top-level function, like len or repr, or some top-level syntax, like the plus sign or the multiplication sign, that allows us to invoke that protocol, and it all fits together in this whole. We can think of this as a protocol in the sense that, like many protocols, when we implement something like len, we do that by delegating back to the protocol itself. So notice, len is implemented in terms of len being called on a constituent object. Add is implemented by adding up some components, namely the coefficients. Repr is implemented by calling repr on some component. We see this as a very common pattern in the Python data model. Every time we want to implement some custom behavior on a Python object, we do it by implementing an underscore function, which ties to some top-level syntax or some top-level function, and we implement it in terms of that thing itself. So for example, if we have some top-level syntax, parentheses coming after the name of an object, and we might call that the call protocol. We'd implement it by implementing the function called call. We could look at the documentation to see any caveats or any special things we have to keep in mind when we implement that. In the case of a polynomial, this may not make a lot of sense. Perhaps to call it means something different. Maybe if we want to have some really horrible syntax where we say P1, P2 means multiplication, we could do that. I can't think of anything more atrocious than that, but perhaps that's what we want. But in any case, we may implement this in terms of calling something else. This is one of the core patterns that we see in Python. This is probably one of the very first patterns that you'd see as a novice Python programmer. In fact, when you look at object orientation in Python, there are 3 core patterns that you'd have to understand to really understand object orientation in Python. This is one of them, the protocol view of Python. The second one is the built-in inheritance protocol and how it works, where you go on a Python object to look for things. And the third one is some caveats around how object orientation in Python works. That's where I wanted to start off with. And for those of you who are just kind of on that level of being effective in Python, these are the kind of patterns that I would encourage you to look out for as you learn Python. I want to go much deeper than this. And I want to jump into a very tricky metaphor using a feature which you may have heard of and you may have been warned against, something you may have seen kind of along the margins when you're using some library. If you do anything with web programming and you use Django, you may have seen this in the ORM, or you may have heard people whispering about this one feature. And I want to bring up this feature for you. I want to show you that it has a very clear and concise meaning, just to illustrate how powerful these mental models are for understanding Python itself and for driving expertise. So let's shelve this for a second. Let's shelve this idea of Python having a protocol-oriented data model. And let's look into a new feature. I'll create a new directory called metaclasses, and we'll talk about metaclasses for a bit. Now, the gist of this tutorial is actually leading you towards 3 features which are far more common and far more interesting than metaclasses, namely decorators, generators, and context managers. There is a reason I want to start you off with metaclasses. It's a feature that everybody is warned against using. They're told it's magical, it makes no sense, it's totally the most complicated thing in the world, when in reality, it is the case of a feature where if you understand what the feature is really about, it is very clear and very obvious for why and when you use it. And it's something that you can kind of shelve away in your mind as, oh, this feature does this, this is why I want to use it, I don't need to use it all the time. So let me show you what a metaclass, or what metaclasses are really about. And I'll show this to you for an example. Now here's an opportunity for you to try something, because I think you'll really appreciate this example if you try Actually, let me do this in a different way. Library.py. So I have two files here. And I want you to actually try this. And I want you to remember, I want you to pretend that there are two groups working on some one piece of software. One group is a core infrastructure group, and they write library code. And the other group is a developer group, and they write user code. The developer group takes the library code that somebody else wrote, and they use that library code to accomplish actual business objectives. The core infrastructure group gets paid a lot of money to accomplish no actual business objectives, but to provide library software that the rest of us can use. Isn't that the story of tech companies? Which team would you rather work on? Nobody has any opinion whatsoever. I'd rather work on the user team because I think that's where some of the more exciting work is. And you're a lot closer where the money is actually being made, so that can't hurt. But some people like to be on the core infrastructure team because they think that the technical problems are often much more interesting than some particular business unit's problem around not getting data in the right format or who knows what. Let's say that this library provides classes. And these classes are expected to be subclassed in the user code. So I'll create a class here called base. And I'll create a class here called derived that derives from base. OK? I've got 5 lines of code on the screen. This is the basic pattern. We see this pattern all over the place. Somebody writes some class in library code, and somebody else has to use it. I'm going to add 2 things, one function on each side, and then pose a question to you. Let's pretend you exist on the right-hand side of the screen. You write user code. You cannot write or alter or modify or in any way touch the code on the left-hand side of the screen. You can use it, but you can't change it. It's library code. You don't have source code access to it. Even if you did, this is being deployed in some environment where any local changes you made wouldn't be preserved. Maybe in the deployment environment, this is pulled down from NuGet or somewhere else. So you have no way to change the code on the left-hand side of the screen. Your only control is code that you can write on the right-hand side of the screen. Where could the code on the right-hand side of the screen break? Very simply, where could this function break? If there is no foo method, exactly. What can you do in your code to make sure that at least, at the very minimum, if the person who writes the library code removes that foo method, your code fails, not at runtime, but at any point earlier than runtime? One very simple thing you could do is you could write a test that just calls bar on your derived class. Very simple thing. And make sure you run your test before you deploy, and you'll see the code fail sometime before it hits the runtime production environment. That's one thing you could do. Anything simpler you can think of. Take a minute and just try and think. Is there anything simpler you could add to this code to just make sure that this code has the ability to fail before it hits the runtime production environment? Doesn't have to, there's not really that same concept of compile time in Python as there is in other languages. But anything you can think of where you could just save yourself a little bit of effort if those core infrastructure meatheads accidentally screw something up and keep you going. You know, I was on a team. I often work in a vendor capacity, working on very small, very narrowly defined projects. I was in a situation on Monday where there was a Sev1 issue, and I was the only person on the team that was thought to be involved with it, who was online. Somebody messaged me and asked me, can you help me with the Sev1 issue? I told them, I have no idea. I work on one tiny, very small, Python-specific, very narrow area. But apparently I was the only one between the manager and the top of the company itself who was online. So I was sitting there just trying to tell people, sorry, I don't know anything. I'm hopeless. Let's see if we can avoid those kind of issues. Let's see if we can avoid, if there's anything we can add to our code so that you don't have to message me and hear me complain to you that I don't know anything and then you see how much I bill per hour, and you're like, well, why are we paying you so much if you don't know anything? What could you do? Any thoughts? I'll give you something really easy. Really easy. Whoops. What does this do? What's happening here? Here, I check to see that that method exists. If the method doesn't exist, I assert the code will fail. So all I have to do is make sure all of my modules can be imported, which does not require a runtime environment. I just import everything. If, for some reason, they broke this method here, they gave it a different name, they called it food instead, I would see this code fail before this class is ever defined, and I'd get exactly what I wanted. I'd have some early warning that this had broken. What we can see in general is that what I'm trying to do here is enforce a constraint. I'm having the user level enforce some constraint on the library level. In other words, the derived class is enforcing a constraint on the base class. The derived class is saying, hey, the base class has to have these characteristics in order for me to run and be happy. And if it doesn't have these characteristics, in this particular case, if it doesn't have this method implemented, I'm going to fail loudly and I won't run. So that's pretty straightforward. Actually, that was pretty straightforward. And it turns out there's quite a few different ways we can do this. This little approach is very simple, very straightforward. But let's flip the script a little bit. Let's say, instead, we have a case that looks like this. Let's say now you're the core infrastructure writer, and you have to deal with those meatheads in the business unit actually using your code and abusing your code and misusing your code. They have no idea what they're doing. And you write your base class under the assumption that some responsible developer in the business unit will go and implement this bar method, because if they don't, everything falls apart. Now, in this example, you exist on the left-hand side of the screen, not on the right-hand side of the screen. You have no ability to change the code on the right-hand side of the screen. Even though you may be higher up in the technical organization, you have no idea where this right-hand user code even sits. Your only ability is to put out library code for people to consume. You have no idea who's even using your code. Even if you could see their code, you might not be able to fix it. Let's ask a separate question, but a very similar question to what we had before. Sitting on the left-hand side of the screen, how do you make sure that the user on the right-hand side of the screen doesn't screw up? How do you make sure that, in this case, that bar method is in fact implemented? Because if it's not, your code breaks, and they're going to blame you. They're going to call this foo method. They're going to see in the traceback that foo method is in your file, and they're going to blame you for getting this wrong. So how do you work the other way? How do you make sure they don't screw up? We can't do the same thing. We can't say assert has adder derived bar. This doesn't make sense on the left-hand side of the screen. We'd have to move that to the right-hand side of the screen, but we're not allowed to touch the code on the right-hand side of the screen. So what do we do? Any thoughts? Turns out there are about 3 common answers to this. One of them is meta classes. There's 2 other answers. Any thoughts?
Try catch.
Where do we put the try catch?
Try the return and then catch.
We could do try here. That would be fine, except this will only occur at runtime. So if we try catch here, it's not really any different than just running this function and seeing the error. We'll still only see the error at runtime. We won't be able to catch it before that code hits production on July 3rd, and then they're calling me up to ask me to help out. And I'm like, I have no clue about. They're like, you're on a team that's involved with Azure Security. And I'll say, I have no clue anything about Azure Security. True story. It really happens. What can we do? Well, if we think about that very first example, we can see that our data model example actually goes much deeper than just that. And the reason that we could call Python a protocol-oriented language is not just because the Python data model, the object model, is protocol-oriented, but that the entire Python language itself has a notion of hooks and protocols and safety valves within it. I want to show you something kind of interesting. One thing that a lot of people who come to Python from other languages don't realize is that Python is a much simpler language than you might appreciate. For those of you who are originally C++ or Java programmers, you have a mental model of in your head for how programming languages like those work. And you have that mental model split between some compile time steps and some runtime steps. And in that compile time step, there's an enormous amount of complexity. If you look at all the different optimizations that the Visual Studio compiler can perform on code, there's an enormous amount of complexity there. Python, it turns out, is a much, much simpler language. Python code runs from top to bottom linearly, and almost everything that you see in Python, almost every statement that you see in Python, with the exception of 2 of them, are actually executable runtime code. In C++ or Java, a class statement is not executable code. In C++, it definitely isn't executable code. In C++, a class statement just says, here's a bucket of bits. Here's how you name portions of that bucket of bits. In Python, a class statement is actually runtime executable code. What does that mean? Well, let's take a look. What that means is that in Python, I could do something like this. Define a class in a loop 10 times in a row. Totally the most useless thing I could ever do, has no effect whatsoever, but I can stick for loops outside of class bodies and redefine classes if I want. Has no use, but it's meaningful in Python. I could do the same thing the other way. Create a bar method under this foo object 10 times. Only one of them will survive. The last one will call all the previous ones. But Python accepts this as syntax because this class statement is fundamentally executable code. Now I told you, and the direction where we started this was talking about Python as a protocol-oriented language. Let's see something kind of interesting. I'm just going to create a function, and I only need this for wrapping purposes. Let me create my base class inside some function. And let me use a function in a module in the Python standard library called dis. Dis stands for disassemble. Let's disassemble this and see what actually happens in the Python bytecode. What we see is something kind of interesting. We see that there's this thing in the Python bytecode called load build class. It's an actual executable runtime instruction in the Python interpreter for creating a class. Well, hold on a second. In the very first example I showed you, I said there typically tends to be in Python some correspondence between some top-level syntax or function and some underscore method that implements that syntax or function. There happens to be some top-level mechanism here. It's not explicitly syntax, it's not explicitly a function for building a class. It turns out in Python, there is a hook. There is an underscore function that allows you to hook into and to do things with the process of building classes. And I bet you can guess what it's called, because just like the correspondence between repr and double underscore repr, len and double underscore len, adding and double underscore add, it's the same thing here. There's a function in Python called build class. It sits on a module called the built-ins. So if I equals my BC. So if I define a function here called, we'll do it like this. If I do this, I'll capture the original build class. I'll write my own build class. I'll import from the built-ins and I'll swap them out. Here, I can patch into what Python actually does when it creates classes. And I won't do anything interesting in here. I'll just print out all the arguments that are passed. Okay? And so let's run our Python script one more time. Python-i user.py. Whoops. And you can see, here's the class that was created. In fact, you can even see I caught another class that was being built, that was probably being built somewhere in the interactive interpreter itself. But the most important one that you can see is I actually can actually catch the building of this class. And you can see there's some interesting things that I'm passed. I'm passed the name of the class, I'm passed its bases, and I'm passed a function, and I'm passed no other arguments. Well, what I can do now that I can see the class that I'm building is I could hook into this and I could do something with it, right? I could add my assert here. I could say if the actual arguments for this are, and this is where I can't remember them, the function, the name, and the bases. Function, the name, and the bases. And I could say if the base, actually it's the base, if the base is equal to this base here, or if it's actually this actual base object, I could check if the bar method is defined. And when I run this, you can see let's pass in any KW here as well. Which arguments does it take? 1, 2. Oh, the third one's optional. Because not everything has to have a base class. And who cares really? This one, you can see I struggle with this one a little bit because we don't typically do this. We say if base is not none. Okay, there we go. And you can see we were able to have a little place where we could check if that bar method was defined. This isn't typically what we do, but it's to show you that this idea of Python being a protocol-oriented language is actually quite a common pattern and quite a fundamental piece of Python. Almost everything that the Python language does in an execution context, like building classes, creating functions, importing modules, you can find a way to hook into that. Once you can find a way to hook into that, you can start doing things that you want to do, like check, is my user code going to break from the perspective of the library author? Now, the reason that I struggle with writing this function here is in part because, first, what's really the most important here is understanding that this pattern exists, knowing that there are options for solving this pattern, and also knowing that this is not the option that you'd ever use for solving this pattern. Build class is available for you to use, but it's not how people actually solve this problem. There are two fundamental features in Python that people use to solve the problem of enforcing constraints from derived class to base classes. The first one is the meta class. Meta classes are merely classes that derive from type, that have some special methods on them, that you'll have to read the documentation to understand all the special methods for, but fundamentally allow you to intercept the construction of derived types. The method that you care about here is called new, and it takes 4 arguments, bases, body, and the name bases in the body. And we'll see where it gives us an opportunity to actually perform our check. Name, bases, body. You can see it got called right here with our derived class. You can see this last argument for the derived class is the body of that class. It's a dictionary with all the methods of that class. You can see in it the bar method. And so simply, to get the behavior I want, I could simply do assert bar, or if not bar in body, raise type error, bad user. Just like that. This is the first answer to the core question. In order to enforce the constraint the other way around, if I can only touch the code on the left-hand side of the screen and not the right-hand side of the screen, I can't just have assert lines all over the place. I have to do something fundamentally different. And the thing I have to do fundamentally different is I have to find a way to intercept how classes are constructed, of which there are 3 common approaches. Build class, which is the least common approach, but works on the idea that Python as a protocol-based language has these safety valves and hooks, even in things as fundamental as the construction of any class. Second, metaclasses, which are just the mechanism by which classes are constructed. That's the approach that you see here. And I'll show you the third one. The third one is just a slight variant on the metaclass approach. When people tell you about metaclasses, typically, they tell you, this is a magical feature. You'll never need to use this feature. It's overly complicated. And the reason that I like to start this session with that, despite its, yes, being a very rare feature, a feature you'll very rarely have to use, is to show you that every feature of Python so far has at least 1 or 2 very clear and unambiguous mental models, is applicable to 1 or 2 very clear and unambiguous metaphors for where it's actually useful. In this case, metaclasses are how you can make sure that if you only control the code on the left-hand side of the screen, you can still enforce constraints on the code on the right-hand side of the screen. You can enforce constraints down the class hierarchy from a base class to a derived class. This is one approach, using a metaclass that just intercepts the construction of the class. And the second is even easier. It turns out that in Python, metaclasses have a bad reputation because even those people who understand where they're useful see that metaclasses have a lot of complexity to them. Part of what I haven't told you at all is any of the syntax of the metaclass or any of the arguments they take or any of the details for how the class hierarchy fits together, because all of that doesn't really matter. When you need to know that information, you'll go look up and find that information. But unless you know why you want to use a metaclass in the first place, it doesn't matter how many details of the feature you need to know. Once you understand where and why you need to use the feature, then the rest of it are just details you'll look up. When you start looking up those details, you'll see that in many of the features I show you, the story isn't that easy. There's always caveats, there's always catches. And one of the catches is this metaclass feature is very clumsy to use. And so in Python 3.6, a new feature was used, or a new feature was added called init subclass. And init subclass, I think it goes here, just gives you a method that allows you to hook into when a subclass of some class is being initialized. And that's it. And I think it goes here. Let's find out. If Brett were here, he could tell you exactly where it goes. Let's remove the metaclass for now. And we'll do one thing, if name. We'll leave that there. Okay, so yes, it got called in the right place. And then init subclass. Okay. Yeah. So this gets called with the self. So the other approach we do is as follows. This was being called on that, and with the init subclass, we have other hooks for figuring out. This one would come in init subclass. You have to remember what arguments it takes, but you can look into it. Really, frankly, it does not matter that much. So this is my simple story about metaclasses. Metaclasses are a feature that we're often told that are an expert level feature. You're not supposed to ever use them. You should shy away from them. You should cover your eyes before you read code that includes metaclasses. And it simply isn't that. It simply is that for all of these advanced features, there's usually one or two very clear metaphors to understand what that feature is all about. And once you understand what that feature is all about, there's a lot of details you need to read through in documentation. That's the approach I want to take for the remaining 3 features I want to show you. The next feature is a very simple feature called decorators. I'm sure some of you have already seen this feature. But I want to show you kind of where this feature comes from. It's a very simple and very boring feature indeed. And you've probably seen this feature before. It's this little at that shows up on top of some function definition. This little at with a dotted name, so you see something like a.b.c. And for those of you who are very familiar with this feature, you might wonder why you can't do this, or why there are limitations to what you can put in the decorator line. The answer for it is a really stupid answer. There is no good reason, but there is a limitation. For those of you who haven't seen this feature before, I want to show you something about Python, something very core and very fundamental about Python. I told you, when we talked about metaclasses, that Python is a live language. There is no separate step that turns function definitions into bags of bits tagged in some ELF binary or some PE binary somewhere. That a function definition is actually a live thing. It actually runs at runtime. There's actually executable code associated with this def. Okay? So let me show you that in practice. Here's a function called add that adds 2 values. Okay? Let me create a little separation down here, and let me run that. And here I have my function add, and I can add 2 values. Now notice, the first thing I did in my terminal is I looked at the function itself, and I got a return value. You can see that the Python interpreter can actually tell me where physically in memory this function exists. And in fact, this add function is an object, and I can ask it all sorts of things, like what's your name? What's your module where you were defined? I can ask it, let's give that a default value there and run this again. I can say add, what are your defaults? And it can tell me what default values it had. I can say, what's your code? Like what code do you contain? This is actually the bytecodes for this add function, and you can see them right here. I could ask it things like, how many local variables do you have? That's your name. There's one more that's interesting, var names. I can ask you what variable names do you interact with? What are the variable names of your signature, X and Y? I can do all sorts of things to interact live with this function. Well, it's interesting that this function itself is a runtime object. We kind of see this, or we might be familiar with this if we're C or C++ programmers. In C and C++, we can have function pointers, but they're really just determined by the compiler. They're just memory addresses that the compiler knows for where it put the bag of bits that represents that function sits. In Java, for a Java programmer or a C# programmer, we might be familiar with runtime classes and functions under those runtime classes. In Python, it's closer to the latter, but much simpler than that. Every Python structure that you interact with, whether it's an object or a function or a generator, has some runtime life, has some runtime existence. You can see it in memory. You can ask it questions like what module were you defined in. You can even ask it very useful questions like if you use the inspect module, you can say, what's your source code? And it'll tell you the source code right back out. So you can see, you can ask the function to give it source code, and it'll give you its source code right back. You can ask it, what file are you in? And it'll tell you what file it was defined in. You can ask it what module you're defined in, or I think get line. You can you can ask it what line number it was defined on. You can ask it all sorts of important questions. Well, there's something interesting that you can also do. Let's say that I have some code here that calls my add function. Maybe it's part of some testing code, or maybe it's some code, part of some application. Let's give it one more example. So you can see I'll add both numbers and I'll also add strings. Okay? Simple enough. Let's say that I want to change my code very slightly. Let's say for some reason this add function isn't quite doing what I want. Or maybe it's doing what I want, but I need to do something like time how long it takes to run. Because for some reason, some of these are much slower than other things. It takes a lot of time to run. I want to time it. And so what are my options? Well, I know in the time module, there's a time function. So I know I can say time, and I can get the time right now. I can do that again. I can subtract them and figure out how many seconds it took. And so how would I time these? I'd say before equals time, after equals time, print time taken after minus before, like this. And now I could kind of profile my code, except this kind of sucks because every time I need to do this, I need to add this in n places throughout my code. I have to add it in all sorts of places throughout my code. There's something missing here. There's something wrong here. When we look at this example, and when we think about decorators in the context of the problem we're trying to solve here, we see another core and important pattern in Python. The Python developers really don't want you to be here today because it's the 5th of July, and they'd rather you be home with your family, spending time with them. I'm very happy that you're here today in this session, and I hope you're enjoying yourself so far. But what I mean by saying the Python core developers don't want you to be here is this. Given the option between writing an absolutely complete, forward-compatible, absolutely perfect solution to a given problem and writing the simplest, stupidest, quickest thing that gets the job done, the core developers of the Python language would rather that you write the simplest, stupidest, quickest thing to get the job done and go home and spend the rest of the day with your family. And the reason that you know that that's true is that when you look throughout the Python programming language, there are a number of examples of cases where you can write the simplest and stupidest thing to get the job done. And when the task at hand becomes harder or more complex or the requirements change, you can change your code in a very simple fashion to linearly extend its functionality without having to rewrite everything from scratch. This is a fundamental difference between writing code in Python and writing code in a language like C++. In C++, there is a lot of upfront design that you need to do in order to be effective. And if you make a mistake in something in your upfront design in C++, you're going to be rewriting a lot of code down the line. Whereas in Python, we'll see a number of different features are orientated around how do we write the simplest thing today, and then when the problem gets a little bit harder, we have an avenue for making our code a little bit more complex. Here we can see a bad example of that. Because in the case where I want the code to be a little bit more complex, I wanted to capture the timings for how long this function took, in addition to the function output, I've made my code substantially more complex. I've added a lot of garbage and I've rewritten a lot of stuff. And you can think the ratio of library code here to user code here, it's usually a lot more user code than library code. It's the whole point of writing library code in the first place. And so, to have 3 times, to have to add code in 3 different places instead of 1 place makes for something pretty gnarly. So the first thing that you might say is, well, I could add that code in just 1 place. I could say something like this. Capture my return value and do the time before and the time after. Print it out here. Like that. And this would be definitely better than before. Definitely better than before. I've added code in 1 place instead of 3 places. But if my library looked like this, and maybe I had examples, if my library looked like that, then I'm still really not in the best situation because I have to add all this tracking code to 2 places. So there's got to be a better way. And in fact, my library could still be very big. And so that still means I have to write a lot of code and rewrite a lot of code. So it must be a better way. Now remember, what did I tell you? I told you that that Python programming language is a live language, that everything has some runtime representation. So both this add function and this sub function have runtime representations. The sub doesn't work on strings. So both add and sub are functions. What could I do? Well, maybe I could write my own function called time, right? Or timer. And I take a function, and I take the x and the y arguments, and I apply this function like that. Simple enough, right? And I do the timing before, and I do the timing after. And I print the elapsed time here. And I return the return value. Okay? Now, I would just have to change these lines of code slightly. I have to change that from a parentheses to a comma, and so on. As long as I could account for the default value. And I have to change each one of these lines as follows. This is a little bit better. Not that much better, but a little bit better. I'll change the first three, and we'll see it at work. So you can see from time, import time. Let's make this a little bit smaller so it all fits on the screen at the same time. And you can see these three were timed, the rest weren't. That's still not that much better. I can still do better. Well, remember that everything happens live in the Python programming language. So couldn't I just create a new function here? Couldn't I define a new function here that takes two arguments like this? And in this function, do the timing, call the function that was passed in, and return this function here. And you can see this here is a wrapper that calls the function that was passed in and wraps it with some timing behavior before and after and printing something out. Couldn't I do that? I can define functions at runtime. I can define functions anywhere. And then, instead of all this nastiness, changing all this user code, I could just say add equals timer of add, and sub equals timer of sub. And you could see it added that behavior across everything. And you could see when I do that, what I'm doing is I'm taking one function, I'm wrapping it with some behavior. I'm taking one aspect or one piece of core or common functionality, and I'm wrapping a bunch of different functions in a really simple fashion. And all I'm doing is I'm creating a new function that takes the original function and wraps it with a little bit of behavior before and after. And that's it. And it turns out that Python wants to make this a little bit easier for you because this pattern of something equals call a function on that original thing, that exists. And that's what a decorator is in Python. A decorator is merely syntax that's equivalent to the line that says this. Sub equals timer of sub. That's all it is. It's syntax that then fits into the ability to dynamically construct a function to wrap this behavior. So this is what our final example would look like. We would have started with code that looked like this. We would have had to add only the timer code and then two decorators. And we'd be able to very easily slip in this extra functionality we want without having to rewrite all this user code ourselves. That's the core of what a decorator in Python is. At its core, it is very simple syntax to just allow you to write an ugly pattern, sub equals timer of sub, in a slightly nicer way, in a slightly nicer place at the top. But fundamentally, it's about allowing you to take this wrapping behavior for functions and to wrap wide swaths of functions in one fashion without having to rewrite a lot of user code or having to even perform a lot of churn on your library code. That's what a decorator is. Go ahead.
So when we have particular parameter pass on
So one of the problems here, I think you're identifying, here I hard-coded the parameters, right? And I even hard-coded the default. The real answer is this is where we use star args and star star quarks. Now, this decorator works on any function that takes any arbitrary set of positional and keyword parameters and just forwards them on. And so now this will work to wrap any function with any set of defaults in any fashion. This is part of why star args and star quarks are so powerful. They're there for to write functions that can take any arbitrary parameter spec and forward it on in any fashion. Was that the core of what you're asking?
Like one more thing I was thinking about, I want to have a retry function. Basically, I just want to have a function that I just want to retry multiple times. But I want to change for this abstraction, I want to retry 2 times versus for add, I want to retry 1 time.
So you want to do something an n number of times? That's easy enough too. So what you want to do, so say you want to have the add just run 3 times in a row and you want to have the sub run twice in a row. What you do, we'll take off the timer decorator. So we want to have some function that runs n times, right? We have our wrapper function in the middle that takes any arguments here and here. And the question is, how do we identify how many times? We're going to add one more level to this. What we'll say is we'll say that n times gives you a decorator. So if let's start this very simply. Let's assume that we always want n times to be twice, okay? We only want to run this function twice. So I'll say for, I'll just say n equals 2 here, for da in range of n, rv equals function, like that. Okay? So here's our wrapper. It'll just call the function twice, capture the value twice, and return it. And return our wrapper, and then we can apply this here and here. Now we won't see this really happen. We won't see the results here, but if we wanted to, you could do this. So you can see it ran add twice here, sub twice there. Now you want to generalize this because you don't want to run it just 2 times, you want to run it some number of times. Well, why can't we just wrap this in another function that takes the n and just return this? Like that, right? And so now this is a function that takes how many times? These are what they call higher order decorators. Really not that interesting or that important. It's a fairly simplistic extension of the idea, which is if you can return if you can have a function that returns a function, then you can have a function that returns a function where that inner function then returns another function. Ad infinitum, going as deep as you want to solve whatever problem you want. There is a very important core concept that is hidden in here, which is what you might call the closure object duality. It's not something that we have time to look at in this session, but it is a very important duality in Python, but it's not one of the topics that we can look at. But just to show you this in practice, you can see this got called twice, this got called 5 times. So you can write your own n times decorator very easily as well. And the core of it is just the idea that you start with the wrapper. So this is just your wrapper function, what you're replacing it with. The decorator syntax allows you to do that replacing very easily. And then in order to get this programmatic behavior, you just add one level, a function outside that constructs a decorator. The decorator then constructs the wrapper then wraps the function itself. It is rare that you'll see a decorator deeper than this, just because it's very rare that you have context. There's typically not an additional context where you need to feed information in that requires you to have decorators deeper than this. So that's a decorator. Decorators are probably the least interesting of all the functions we're going to look at, or one of the features we're going to look at. The next feature I want to look at is called generators. Now, some of you may already know what a generator is. Generators are a very interesting and very powerful feature of Python. They're also a feature that include, where I feel the mental model is often very limited. What people understand of the mental model is often fairly limited. There's more to it than just what you might call the eagerness versus laziness divide. But let me start you off with something more fundamental than even that. I told you before that there is always some top-level syntax or function and some underscore method that implements it. So I told you, if you have parentheses after something, this is what's called the call protocol. So there's some method call that implements it. I want you to tell me what's the difference between this and this. What's the difference between add 1 and add 2? And I'll even create a terminal down here, and I'll add 1 adds 2 numbers, add 2 adds 2 numbers. From the outside, what's the difference between these two? You wouldn't, unless you started peeking inside, unless you started saying, what are you? Add 1? Oh, you're a function. What are you? Add 2? So you started peeking on the inside. Oh, you're a class. You wouldn't be able to tell the difference. Functionally, there's no way for you to distinguish between the two. In fact, add 1 behind the scenes looks very similar to add 2. It's just that syntactically, it's a whole hell of a lot easier to write. So from the perspective of actually writing the code, you're always going to want to do it this way. Now, there is a fundamental difference, which is if you wanted to start adding some stateful behavior, like this, right? If you wanted to add that, then clearly there's one way to do it for the adder, and there's another way to do it for the function. So one way to do it for the class and one way to do it for the function. And this is the aforementioned, what I hinted at, this object closure duality. There's actually a couple of different approaches you can think of for how you do this. The core idea here is that fundamentally there is some very nice syntax and then some object model that everything kind of sits in. And this is closer to what the object model itself looks like. You can think that add 1 is some object that kind of looks something like this, although we'll remove the statefulness stuff, just so that the two examples are at parity. Let's think about this in a different way. Let's think about some function that takes a lot of time to do something, right? Maybe a function that goes off and performs network requests, and it needs to load data from a database. What would that function look like? Well, it might have the resulting rows, and it might say, while db.read rows.append something. Now, this will be a little bit tricky for us to actually demo, so we'll do a couple of simplifications just to make this code look, kind of mimic what long-running computational code looks like, but without actually having to use any fancy libraries. So let's say what we have instead is we have some code, and it just sleeps for a half a second every time it provides a return value. And the return value will just be a number from 0 to 9. Let me ask you a question. And we'll just call this compute. Whoops. When I call compute, how long does it take to run? Five seconds. What if I only care about the first return value? What if I only care about the first value? How long does it take to run? What if I care about the first 3 values? How long does it take to run? How much memory, in terms of, if we just make very simple assumptions, how much memory does compute require? 10 units of memory? 10 integers in a list, right? What if I only care about the first value? How much memory does it use? Same, right? What if I care about all the elements? How much memory does it use? Same. This is what we often mean by eager. The idea that this function, irrespective of what you actually care about in this computation, always takes the exact same amount of memory and the exact same amount of time. It eagerly gives you the entire result, and you're sitting there waiting for the entire result. So you can see it gives me the entire result all at once. This is undesirable because if this happens to be not 0.5 seconds, but 5 seconds, then I have to wait 50 seconds before I can even start processing the very first entry. And so I'm sitting there blocked, waiting for 50 seconds, when maybe I could process these one by one. Also, if this is not 10 entries, but 1,000,000 entries, maybe I only want to look at them one by one. I don't need to have the whole history of all the entries. I'm now spending gigabytes of memory just so you can eagerly give me the entire result set, when I only care to look at them one by one, and the moment I look at one of them, I could throw it away. So you can see this is both wasteful from the perspective of the time that it takes, and wasteful from the perspective of the amount of memory it takes. Let's think if there's a better way to do this. And let's think about this in terms of our object model. Let me rewrite compute as a class. So it doesn't take any arguments, and I'll just dump this stuff underneath. Nothing very interesting here, but more or less does the exact same thing, really no difference between the two versions. So I haven't gained anything here. I haven't gained anything by feeding it into my object model. That said, I've kind of seen this pattern before. I've seen this pattern of I only want one element at a time, and I'm going to get each element, and as I get each element, I'll process it and maybe throw it away. It's a basic looping construct. In fact, I see it even here in this looping construct here. I don't get the entire list at once. I only get each one individual element of the list. And one thing that we might know is that in Python, we see top-level syntax or top-level functions has some corresponding underscore methods that implement it. If I told you that there's a pattern, if I told you that there's some syntax for x and xs, and I told you that this syntax actually looks like this, more or less under the covers, you could probably guess what the underscore functions we have to implement would be. They'd correspond to these two top-level functions here and here. They'd be iter, and they'd be next. So what that means is we can take a class in Python, we can add an iter and a next method, and suddenly that class can be iterated over. Well, in the process of that iteration, what could we do? Well, anything arbitrarily, including perform a long computation. So what we could do, and what the iter method actually needs to return, you'll find out when you read the documentation. It's not that important. We'll just return self. The next method just gives you each next method that you iterate over. Well, instead of putting the computation in this eager call method, what if I did this? What if I have the iter method say the last number I looked at was 0, and I do this. I say self.last plus equals 1. If self.last is greater than, and we'll limit this loop back to 10, just to keep our lives sane. It's greater than 10. Raise stop iteration. Otherwise, we sleep for 0.5 seconds, and we return self.last. And we'll actually do, this will be slightly different, so we'll do it like this. Here. So there, this will give us the same thing. So now, slightly different order, but you can see now our next method computes what was the last value we looked at, captures it, it increments the last value we looked at. If there's too many, it raises a stop iteration. We won't worry about what that means just yet. It'll sleep corresponding to our long-running computation, and it'll return the value. Now notice something different between this compute method and this next method. This compute method returned a list of all the values. This next method returned a single value. And the way that you'd use it is as follows. You just print it out. You loop over and print it out. And we'll actually see that here in practice. You can see it's computing each value one at a time. And in this loop here, you can do something you want with it, like print it out. It still takes 50 seconds in total to print out the whole thing. But you only pay for, or it still takes 5 seconds in total to print out the whole thing, but you only have to pay for 1 unit of computation before you can start using that value. And it no longer requires 10 units of memory because there's no storage anymore. Notice, here, there's no storage, and here, there's no list, there's no storage. Well, this really looks ugly, and this is really hard to read. Just like this looks really ugly, and this is really hard to read, and there's a much simpler way to write it, a much simpler formal expression for how to write functions. There's a much simpler way to write a function that operates in this fashion. And that's what the generator syntax is. The generator syntax is merely something that looks like this. And all this means is this thing here, compute, is something that can be iterated over. Each time you iterate over it, this is the value that it will yield. The stop iteration naturally happens because if you try and iterate over this too many times, there'll be nothing left to yield because you'll have fallen off the end of this block here. Its state is maintained internally. It's just a function that kind of doesn't really return eagerly. You'd never want to write this formulation. This is just such a pain in the butt. You'd instead want to take the original function formulation and write it in its generator formulation. When you look at the function formulation and the generator formulation, and you squint your eyes, you can see all the same pieces in the same places. Except in one of them, you have storage, and you have eager computation of the entire result set. And in the other one, you have no storage, and you're simply returning values as you see them. This is the core concept behind a generator and the core mental model behind a generator. That instead of eagerly computing values, you give them to the user as they ask for them. But there is another similarly important and critical core concept to how generators work, beyond just this. And that's what I want to show you leading up into our last example. We have all seen APIs that look like this. Run this first. We've all seen APIs that look like this, which have methods that indicate the order in which you have to run functions. If you don't run this first, everything blows up. If you don't run this last, everything blows up. And in the documentation, they tell you, please run this method, then this method, then this method, because if you do it in any other order, all hell breaks loose. Unfortunately, this API is kind of lying to you because nothing stops you from being a dunderhead, so I don't like the word dunder, and doing this. Nothing physically stops you from putting these in the wrong order, other than that you fail to read the documentation, and you'll see it break. Well, one interesting thing about the generator formulation is that if you look at the generator formulation, you can see it performs some computation, then not only does it yield the result back, but it also yields control back to the caller. You can see here in this formulation, let's lowercase this, I perform one computation, one long-running computation modeled by this sleep. And then I give the value back to the user to do something with, and then they ask for the next computation, give it back to the user to do something with. So I'm kind of interleaving the user code and the library code. In the eager formulation, the library code ran to completion, gave the entire result set back to the user, then the user did whatever they want with it. In the generator formulation, I have a little bit of library code run, then a little bit of user code run, then a little bit of library code run, then a little bit of user code run. And I interleave them. This is the actual core conceptualization behind what the generators are built upon, the idea of coroutines. Subroutines we can think of as any piece of executable code that runs from some starting point to some ending point to completion. They have one single entryway, and they have one single entry point, and they have one single exit point, and that's it. They run, they're done. If you look at how user code and library code interact, if the subroutine is in library code, it runs to completion, and then the user code has to pick up. For the generator, or the coroutine, you enter the generator, and as you ask for values, the generator runs, but you can have this nice interleaving, where some user code runs, asks the generator for a value, the generator runs its code, yields back to the user code does whatever it wants, goes back to the generator, asks for another value, and so on. So you have this interleaving of the two pieces of your code, the user code and the library code. Here in this API, what we'd actually have is, similarly, when we use this API, we'd ideally want to have some interleaving. Because if we could run all three of these methods all at the same time, the API would never have provided us three methods. If we didn't have to have some code between these three calls, they would never be provided as different calls. If they could all be done at once, we would just have one method here called doIt that just calls first, second, and last, and make sure that we can't screw this up. So the reason that the API gives us these three pieces split into three parts is because they specifically intend us to interleave code. They just want to make sure we interleave code in a fixed sequencing, in a fixed order. Well, let's think about this. If I wrote this as a generator, we could do that interleaving while maintaining the sequencing. And this, I would say, is maybe even a more critical mental model for generators than this eager versus lazy divide. The idea that generators are a mechanism by which you can create code that can interleave with other code and also enforce sequencing. Notice here that what happens when this generator runs is it'll run up to this point, yield no value, but it'll yield control back to the caller. Then the caller can resume, and the caller can resume. In this particular formulation, first, second, and last will always run in that order. You can't guarantee that last will run, but you never can guarantee that someone could pull the plug before that runs. But here, if the API were provided in this fashion, you could guarantee that the last method was never called before the first or the second method. The generator forces that sequencing on you. And it forces that sequencing on you because the generator is ultimately a coroutine that allows you this interleaving between two types of code, user code and library code. Let's remember that, and we'll go into the final of the examples we want to look at, the context manager. Context managers are a very, very simple metaphor, and a common metaphor you see all over the place. If you're a C++ user, you've seen this metaphor before. You probably called it resource allocation is initialization, or something like that. If you're a Java programmer, you've seen this metaphor before, but I don't know what you call it in Java. I don't know if Java has a real name or concept for this. It's the idea that there's always some desire to do some setup and teardown, and you want to combine them. If you're a Python programmer, and you've done even very introductory stuff with Python, you've seen a context manager before. And it looks something like this. It's the most basic context manager that you've seen before. You open some file. And the reason you use a context manager here is that there's some corresponding setup and teardown. If you open the file, you got to close the file. This is especially true on Windows because on Linux, file locks are a little bit less aggressive. On Windows, if you don't close the file, you might not be able to delete it later. This is especially true if perhaps this file is backed by some storage where it's not necessarily automatically flushed, if there's some I/O buffering, because definitely, if you open the file and you write to it, you want to make sure those are flushed to disk in case the program terminates at some point with unflushed I/O buffers. You might lose things that you intended to be written to disk. But fundamentally, there is this metaphor here, this idea that we have some setup action and some teardown action, some initial action and some final action, and we want to match them together. Let me show you an example of that. It goes beyond files, but it can go even into things like SQLite databases. So in SQLite, we have these file-backed databases. The connect method is actually a context manager itself. So here, I connected some database. I have some cursor on that database. And let me just do this. And I could do some statement. So I could do something like create table points, x int, y int. I have some statement to execute a table, maybe insert some things into this table. X, Y, values 1, 1. There we go. And then I have some statement where I could select from this. There we go. And then we can commit this. So here we have just very simple use of a context manager, wrapping some database operations. And what is it? It's not cur.commit. We don't need that, actually. And what we'll do is we also want to make sure that we drop our table when we're done. There we go. And so you can see the code ran. I'll do 2 selects just so you can see everything. And you can see our code ran. Now you can see that the idea of there being some setup and teardown action is pretty clear with the opening and closing of the database, right? Obviously, if we open the database and we write to it, we want to close it. But there's another setup and teardown action that you might not see here. See if you can spot it. If we assume that we did something and we want to have some corresponding action to undo it, what's the pair that you see here?
The table?
Yeah, I create a table and I drop a table. Now, naturally, if we were to really properly do this, we'd probably do it in a transaction, and a transaction would give us the right semantics. But let's assume that for SQLite, we might not have transactional support, so we have to be in charge of that pairing, that create and that drop. And naturally, it's a very natural pairing. You create something, you drop it. You want to make sure that both of them get done, irrespective of some error pops up in the middle. So how do we actually write our own context manager? And you'll see that this will bring together everything we've looked at so far. As I told you, it turns out, fundamentally in Python, there is always some top-level syntax or some function and some underscore methods that implement it. If I told you let's write it like this, ttx as x. If I told you that behind the scenes, this actually looked like the following. X equals ctx, enter. Try, finally. If I told you that, and I don't know what the argument, there's some arguments that get passed there, I don't care what they are. But if I told you that's what it looks like, you even know exactly what the underscore methods are. They're right in front of your face, right? Enter and exit. So that's how we write a context manager. We implement enter and exit. Now here you're going to see me really fumble because I don't remember any of the arguments that get passed there. But let's try this. So we're going to create a temp table context manager. And we know we need to implement enter and exit. Right? And this takes some other arguments. I don't really care what they are. And we know maybe this temp table needs to take, just for this thing to work, we'll need to initialize it with a cursor. Okay? And then the enter just executes this statement. And the exit just executes that statement. Except this is self.cursor and this is self.cursor. And that's it. We have some enter code and some exit code, and I just move things around to fit it into the protocol. And then the next thing I do is I just tab these over, and I say with temp table cur equals with that cursor. Fair enough? There we go. So let's see that in play. Seemed to work. Let's run that again. Seemed to work. Let's run that again. Seemed to work. If the table weren't destroyed, then I would get an error there saying table already exists. So clearly the enter and the exit are being called. I can even show you that more explicitly. This seems really, really uninteresting. So where is he going with this? I wonder. See, there's the enter and the exit. Pretty straightforward. Now, I wonder why I brought this one up. Because context managers have such a clear and unambiguous metaphor behind them. Why would I take almost a third or a fourth of our time to talk about context managers? I want you to see something kind of interesting here. Kind of interesting here. Can the exit be called before the enter? Should it? Nope. So the enter should always be called before the exit, right? What does that tell you? There's some sequencing. What does that suggest to you? Generator. Because we just saw generators are about sequencing. Maybe I can improve this example by using a generator. Because here, you can see there's an enter and an exit. The enter has to be called before the exit. There's some sequencing. Necessarily, that's what generators are all about. So let's do it like this. Let's move this up here. Let's move this down up here. We'll put a yield in between the two. And here we'll just say temp table. We'll call this a context manager. We'll say temp table self.cursor. We'll create an instance of this, and then we'll just do next self.gen. I think that'll work. And then return self. Oh, and we have to do context manager. We have to do another next in here. And then we have to just do one tiny thing here. That doesn't really matter that much. So there we go. We see everything still works. So we'll put our little enter and exit print statements just to see them still running. Enter up here, or we'll actually make this a little bit better. We'll say created table print dropped table. Just add our little logging statements in there just so we can see them in our code. Create a table, drop table. So we can see how this conceptualization of generators as sequencing is very useful. Now, this is not sufficiently general for my purposes because you can see I kind of hard code what the generator is. So let me just do this. I'll just have it initialize what generator I want to use. The enter. Notice I have a callable function here. So what I'll do is I'll just add in a call here. So I can get some arguments, which will be the cursor, or maybe the args and the quargs. I'll just capture those. On the enter, I'll call my generator with the arguments that I was passed. And I'll get my generator instance. And I'll forward it here and here. So now I can say context manager of temp table. I can call the cursor there, and then I have something that'll work. Now, let's see if that works. And then this has to return self. And then this should be self.quargs. Okay, there we go. So we can see this still works. Now you might wonder, why did I go through all this effort? Well, I want to show you something kind of interesting. This line here looks really ugly. So here, why don't I just do this? Just move my code around a little bit. Take that line here, and I'll just say temp table equals context manager of temp table. You can see what I kind of did was I took my generator and I wrapped it in some object that just kind of fit in the parts of the generator to the enter and the exit, right? That's all I did. And now I can just say with temp table of cursor, right? This will kind of, haven't we seen this like a couple minutes ago? Ever saw that pattern before? Anyone seen something like that? Anyone seen some really useful Python syntax so you don't have to write that? You take some object that happens to be a function, you pass it to another thing that gives you something else, and that rebinds it. Anyone seen this syntax before? I can tab back to the panel. It's only 2 back. What is it? What would we do here? Why would we not write this? Because we have a simpler syntax. What could we write easier here? Anybody? Decorator. So you can see it works without the decorator, but we'd probably just write this like that. Right? Oops. It still works. Well, it turns out all this garbage up here, we don't have to write. It's already been written for us. It's in a library called ContextLib. And it's just a decorator that turns a generator into a context manager. And the only things that we need to make this work completely is that. Here in this example, I want to show you something. This is an example that combines 3 core features of Python together: generators, context managers, and decorators. It does it requiring that you know a little bit of the details of how each of these work. But fundamentally, what we can see is what we have here is 3 features with very clear conceptual meaning, orthogonal conceptual meaning, where each of those pieces of conceptual meaning kind of fit together. A context manager is merely some piece of code that pairs setup and teardown actions, so that the teardown action always occurs if the setup action occurred. A generator is merely some form of syntax that allows us to do things like enforce sequencing and interleaving. Notice the context manager requires interleaving because the setup is interleaved with the actual action you do in the block. You do the setup, then the action in the block, then the teardown at the end. There is that sequencing where the setup, the enter, has to be done before the exit. So it makes sense to have a generator here as well. Finally, we need something to adapt the generator to this data model that we looked at the very beginning. We have these underscore methods, and we have to find some way to take how the generator works and fit it into those underscore methods. One of the things we need to do in order to do that is we need to take this generator object and wrap it in some fashion. That wrapping is part of the core of how Python works. It's easy to dynamically construct functions and have those functions wrap other functions. That's part of the core language itself. It's not really something that we could even lift to the level of being a feature. It really is core to how Python itself is written. However, there does happen to be a feature called decorators that allows us a nice, convenient syntax for doing that exactly. So what you can see here is an example of everything except meta classes and how they all fit together, and how some of these core pieces of Python fit together to write what you might consider to be more nearly expert level code. What I can tell you is that in Python, expert level code is not code that uses every single feature. It's in fact not code that even uses that many features of Python. It's code that has a certain clarity to where and when a feature should be used. It's code that doesn't waste the time of the person who's writing it, because they say to themselves, I have this pattern, Python has this mechanism, I fit them together, and everything just seamlessly and very smoothly works. It's code that doesn't have a lot of additional mechanisms associated with it. It doesn't have people creating their own protocols. It doesn't have people creating their own frameworks, where the language itself provides the core pieces that you need, and you merely have to understand what those core pieces are, what they mean, and how to assemble them. So over the last 90 minutes, I've showed you a couple of details of how Python itself is designed, and 4 features that you've probably heard of that Python is known for. 4 features that you might associate with features that an expert would know. Or at least, if you go and interview for a Python job and you say, I'm an expert Python programmer, these are 4 features that you're going to be asked about more likely. The question here is, does anybody remember any of the syntax they looked at? Probably not. Even I don't remember it, and I'm giving the talk. And I have notes here. I have like a cheat sheet. The real answer here is the notes, the details, they do matter. They matter very much. You can't write the code unless you know the syntax. The code won't compile, it won't run. However, what is far more important than the names of the arguments that get passed to exit, or the specific fashion in which different numeric underscore methods get dispatched, whether you do radd or add, depending on which is the most derived class. All of those details are actually secondary to a core conceptual understanding of what these features mean. So what I can tell you as the real lessons from this session were as follows. Python is a language oriented around protocols. There's some behavior, some syntax, some bytecode, or some top-level function. And there's a way for you to tell Python how to implement that on an arbitrary object via underscore methods. That exact correspondence is usually guessable, but if you can't guess it, Google Python data model, and you'll find all the different methods and all of the caveats of their use. Python is a very simplistic language in terms of its execution model. Code runs from top to bottom, and things which would not be executable statements in other languages, like class statements and function definitions or generator definitions, are actually executable code in Python. Because they're executable code, not only can you do things like hook into them, but you can also do things like define functions within functions based off of runtime data, define classes within functions based off of some runtime information you have. How these impact specific features. Metaclasses is merely some hook into a class construction process. Because classes are constructed at runtime, you can hook code in there, and because you can hook into the creation of subclasses, you can ask the subclass certain questions like, do you have these methods implemented? That's what they do, that's the mechanism, but the meaning behind it is quite simple. You have library code and user code. When you sit on the library author side, how do you make sure the users don't screw up? How do you enforce a constraint from the library code to the user code? Well, all that it takes is some way to hook into the process of how user classes are instantiated. That's merely what the meta class is. You find that place where you add that hook, you add the check that you want. Oh, make sure that you have the bar method implemented. And you solve the problem. In fact, in the Python standard library, there are regularized solutions to problems like that. In collections.abc, there is an ABC meta class that allows you to use decorators to mark certain methods as abstract methods so that you don't have to write the meta class yourself. And you could think this is a pattern of what the meta class is doing. In fact, almost every example of a meta class that you'll see will be this pattern of some base class and some derived class, the base class trying to enforce a constraint on the derived class. It's almost every pattern of the meta class that you'll see where that meta class is justified. Of course, you can misuse them to do all sorts of crazy things. You can use them in places where it doesn't make any sense. But in the justified uses of the meta class, that's what it's all about. For the decorator, it really isn't anything that interesting. Just a little bit of syntax to allow you to write one line of code a little bit nicer. To take one line of code that you'd write after your function definition and put it above your function definition. But it hooks into this idea in Python that everything gets constructed at runtime, so that when you combine that with the ability to define functions within functions, you can use this in order to wrap sets of functions with some before and after behavior. If you've been around long enough, you might recall this was the whole aspect-orientated idea. But the idea that, can I take a function and wrap it with some behavior, such as timing, capturing the time before and capturing the time after. Or doing things like authentication or logging, anything where you don't have to go into the function itself, you just wrap the behavior around it. Generators are merely a way to take a single computation that would otherwise run eagerly from the injection of its parameters to the final computation and interleave it with other code. By adding yield points where you can yield the intermediate result values or one small piece of the computation, and also yield control back to the caller. In that vein, you can think of a generator as being a way to take one long computation and break it up in small parts where the computation can run a small subunit of that computation. Then your user code can step in and do whatever it wants. Maybe it will use a partial value or use one of the first return values. If you're returning a sequence of return values, it might use each of the individual values. And in that fashion, you can have greater control over how much of that computation actually runs. Do you run it all the way to completion, or do you only need to run it to grab the first 5 values you need? You also have greater control over how much memory is used, because the generator can just yield the values back to you, and you can choose which of those return values you want to keep, which of them you want to throw away. Context managers are merely some structure for allowing you to tie two actions together, a setup action and a teardown action, and make sure that they always happen in concordance with each other. If the setup action occurs, make sure that teardown action occurs, even if some error happens in the middle. And when you think about these features, and you realize they're related, but mostly orthogonal, you can combine them in interesting ways, like you see in this example here, where you have a decorator, a context manager, and a generator all coexisting and serving exactly its one purpose. As I said at the very beginning, the syntax doesn't matter. The details won't matter until you need to use them. What I want to leave you with, especially since a lot of you are not already very fluent Python programmers, I want to leave you with this idea. Remember what these features are about. Remember what they're for. That's something that you should be able to remember longer than the exact details of the syntax, or even implementation details. In fact, the implementation details and the details of the syntax will change over time. Some of the flaws of the implementation may get fixed. Other details will be fixed in other fashion. But the core meaning behind these is something that will last and will guide you towards writing expert-level Python code far better than memorizing just a bunch of features ever will. So that's my presentation. I hope you enjoyed it. Thank you very much for being a part of it. Any questions? In the back?
So in the yield context, we always mix.
A little louder, please.
So when we use yield or generators,
Yeah.
everything is happening sequentially. Is it possible to look ahead? Like say I'm running a loop which is doing some computation, and can I use, like when I use yield, it basically continues to do the earlier processing?
Yes. So the idea is what you've immediately jumped on is this idea that you can interleave. What you've, I think, jumped onto is the idea that, well, while I've returned control back to the calling context, can I have the original context keep working?
At least like
because
get
then
the
it could
next
kind of
value.
sit in the background and do some work, and then by the time I go back to the generator, I can go and ask it for some value, and it doesn't have to do anything because it's already in the background done that. Well, yes, you can. You could have the generator start its own thread and maybe do things in its own thread. That's entirely possible. And that wouldn't be part of the generator syntax itself. The generator itself is not intended for interleaving in a concurrency mindset. And so where you see generators used as part of this broader idea of concurrency in Python is that the generator mechanism and its syntax have been further refined in Python 3.6 to this asynchronous coroutine syntax. There are many reasons why strictly simultaneous running Python code is something that has been avoided for a very long time in Python. You must have heard of the global interpreter lock and some of the limitations of the global interpreter lock. Accepting that as a limitation, the approaches that people take in concurrency in Python, where they mean single in-process concurrency, are typically either threads, and they ignore the global interpreter lock, or they just allow for strict interleaving of code where, it's all single process, so it's all single-threaded. One greenlet sleeps while the other one runs, and you don't have strictly concurrently running greenlets. That's closer to your answer, which is generally no, the generator is not for this kind of multi-threaded equivalent approach. It really is for this one runs, then this one runs, then this one runs, then this one runs. And that's considered to be the preferred approach for concurrency in Python, where the concurrency is I/O bound. Go ahead.
When you were talking about meta classes,
Yeah.
So you were referring to the runtime checks versus otherwise.
Yeah.
So what would be the point in time the other asserts or validations would happen?
So the problem is runtime checks require you to have the code deployed in a runtime environment. So you'll never know the problem until you hit that exact code path. The whole point of this is, can we any sooner than when it hits that code path in a deployed environment, catch the error? Any kind of run, because Python doesn't have a very strong compiler, it has a very small, that compiler doesn't really do a lot, it's going to be very difficult. However, what we can think of is that module import time is an equivalent to compile time in Python. So just being able to import a module is something that we can do before we hit the runtime compile context. We can do it at our laptop, and if the module imports normally, then we can say, okay, this code will be safe in production. All of the checks that we looked at there were checks which we could run by just sitting at our laptop and importing all of our modules. If it worked, we'd say, good to go. Another thing that we could do is maybe run a unit test suite, but that might be one level deeper than these checks. Because you can think the unit test suite is going to take a lot longer to run, and it might have some mocking of data and moving things around. So what we might have is some checks in the file itself, import everything, okay, good to go, then run our unit tests, okay, good to go, deploy it to production, and then hope that somebody's online who knows how to solve the problem when something breaks.
Quick follow-up on that. The init subclass, is that still runtime or is it?
Init subclass is a runtime check, but everything that runs at the module level is run at runtime. It's just that there are different runtime scopes in Python. So init subclass will operate in the same fashion as the meta class. It'll merely just another place that you can hook into the initialization of a subclass. And you have to look into the details. I thought it took different arguments than it does. You'll have to look into the details to see what arguments it takes and how you actually use it for this purpose. There's a lot of these details of these features, unless you're really, hopefully you're not somebody who's constantly using them, and unless you're constantly using them, the details are things that are easy to forget. But if you know where to look, or you know what to look for, those are details that you can very quickly pick up. And frankly, init subclass has only been around since 3.6. A lot of these details do change over time. But the core models, the core mental models have not changed since these features were first introduced. Even the extension of generators for coroutines and for asynchronous programming, the core mental models behind it haven't really changed since they were first introduced in Python 2.6, 2 whatever. Any last questions? Okay, well, I hope you enjoyed the session.